All right, everyone, I hope that by exploring with that applet, you all came to the conjecture, at least, that the velocity exactly at time 1 should be 2 meters per second. And you did that by, in the applet, making the intervals smaller and smaller and smaller, and noting that the average rate of change got closer and closer and closer and closer to 2 meters per second. Now we want to use calculus to actually prove that. So as we mentioned, what you were really doing is you were computing an average rate of change from time 1 to an unknown time 1 plus h is the letter I'm going to use. Some people will use delta t to represent change in time. That's fine. Over the change in time on the bottom, which is h. This is like saying 1 plus h minus 1, but the 1's cancel, so we just get h. So we'd like to figure out what this is. So remember, our function was f of t equals t squared. So I'm going to need to do 1 plus h quantity squared. And if we'd FOIL that all out correctly, we're going to get 1 plus 2h plus h squared minus 1 all over h. Now remember, we're thinking about h getting really, really, really close to 0 here. Luckily for us, something nice will happen on the top, and these 1's will cancel. And both terms in the top now have an h in it. Because I can't plug in h equaling 0 at this moment, because then I'd be dividing by 0, which we know is not allowed. But now on the top, since each term has an h in it, I can factor an h out of the top, and I get 2 plus h over h. And then I can cancel those h's, because remember, we're not letting h equal 0, we're just letting h get closer and closer and closer to 0, and imagining what that limit will be. So it is legal to cancel that h. And now we have 2 plus h. And let's just pause for a moment to see if this agrees with our answers from before. When we did the interval from time 1.1 to time 1, the answer that we got was 2.1, which is the same as this, because if we're going from time 1.1 to time 1, that's like saying h is 0.1, and we would get 2 plus 0.1, which is 2.1. It works in the other direction as well, because this didn't say anything about whether the h had to be positive or negative. When we were going from time 0.9 to time 1, that was like saying that h was negative 1/10. And if h is negative 1/10, we get 2 plus negative 1/10, which is 1.9. And if you check back in your notes, 1.9 meters per second was the answer that you got for that. So now we're going to say, what happens when h goes to 0? There is so much going on in this little symbol here, limit h goes to 0. In your mind, you have to be imagining h being 0.1, 0.01, 0.001, 0.0001, and the negatives of all of those. All of these infinitely many h values that are getting closer and closer and closer to 0. And in your mind, you have to ask yourself, as that happens, is there one particular number that this quantity, 2 plus h, gets closer and closer and closer and closer to? And the answer is yes. And that quantity is 2. So the instantaneous velocity at time 1 is exactly 2 meters per second. So if this hummingbird had a speedometer on it and it looked down at the speedometer right at time 1, the speedometer would be reading 2 meters per second precisely. That is our first instantaneous rate of change that we've computed. I hope you're excited about that. Let's think about what we did graphically here. We had our graph and we kept taking, and it's harder for me to do this on the board, that's why the applet it's much better for this. But as you slid these points closer and closer and closer together down here, I hope what you saw was that the secant lines were converging on a tangent line, and the slope of this tangent line was exactly 2, the line that just grazes the curve there. And you remember from last week, tangent comes from the Latin for to touch. So the secant line cuts through the curve, because that comes from the Latin for to cut. This just grazes the curve, just touches the curve, and the slope of that tangent line ends up being exactly 2. So did we really compute the velocity just using one point? If all you had was a snapshot of the bird, and you saw that this is where the bird was at time 1, would that be enough to know that the velocity of the bird was 2 meters per second? No. In fact, from this picture, you wouldn't know if the bird was going up, going down, just hovering constantly. We used the entire formula, f of t equals t squared. We put in infinitely many numbers as the values got closer and closer to 2. In other words, as h got closer and closer to 0, we took account of all of those infinitely many values on this curve in order to get our answer of 2. We did not just use the one point. If you just had the one point that the bird was at height 1 at time 1, there's no way to answer the question. We needed the formula for the position. And you might have noticed that this number 2 ends up being exactly halfway between your estimates of 1.9 and 2.1. That's a sort of just good luck feature of the fact that we used a quadratic formula for the bird's height. If you use other formulas, that doesn't happen. So for example, on your homework, you get to do one with a cubic, and then you'll discover that that would not be the same case there. But for any quadratic, it does happen. All right, that was exciting. So we've computed the velocity at time 1. And what if you wanted to compute the velocity at time 3 and time 27 and time -2? You could go through and do the same thing, right? And just keep replacing these ones by whatever the new number was. But after you've done that a few times, I hope you would start to think that this is getting to be a little tedious and annoying. We'd like to come up with just one single formula that works no matter what the t is. And so that's what we're going to try next. What would be the instantaneous velocity at an unknown time t? So we can do the same thing here, except that instead of specifically choosing 1, we'll just put in a t there. So we're going to have to do maybe a little bit more work, but the reward will be much greater because we'll get a formula that works at any time t. But the algebra about this should be pretty much the same. So we still have the limit as h goes to 0. Our function is still f of t equals t squared. So we feed it t plus h. You have to square out t plus h squared, foiling it all out correctly. T squared plus 2th plus h squared. And then f of t is still t squared. And this is all over h. And just to remind us, what we're doing here, this is the change in the position, change in the height over the change in time, which is why we're getting velocity. Just as the 1 squareds canceled over there, the t squareds cancel here. And we again, by great good luck for us, see that both terms in the top have an h in them. So we can factor an h out of that. We get 2t plus h. We still can't let h go to 0 because that would mean dividing by 0. But because we were able to factor that out, they cancel. And so now we have the limit as h goes to 0 of 2t plus h. So you should ask yourself, as h gets very, very small, what happens to 2t? 2t doesn't care what h is doing because 2t doesn't have any h's in it. So 2t just stays as 2t. But this h goes to 0. So this should give us the velocity at any time t that we plug in. So let's see if it agrees with the answer we got in the first case. There we specifically knew that t was equal to 1. So if we plug in 1 here, we get 2 times 1, which is 2, which is the same thing that we got in our example when we specifically knew that t was 1. So what this means is that now I can go to any point on this graph. I can go over here to t equals 3, and I will know that the bird's velocity at time 3 should be what? What should the slope of that tangent line be? It should be 2 times 3, or 6. I can even go back to a negative number, like -2. And I can say, what's the bird's velocity at time -2? And the velocity there will be -4. You can say, what's the velocity at time 0? Then we get a perfectly horizontal tangent line, because when I plug in 0 to this, I get 0. And you can try to convince yourself that none of these velocities will ever repeat. The bird will never have the same velocity twice. And any velocity that you think of, the bird will eventually get to that velocity. Is there a time when this bird's velocity is 1,000 meters per second? Sure, as long as you go off to m equals 500, then the velocity will be 1,000 meters per second. Now, this might not agree with what happens in the real world, but this is the formula. This allows us to take any value of t that we want. And we have an applet that will allow you to explore this graph, drawing tangent lines on it. So I encourage you to explore that applet, and then we'll come back and we will come up with an official definition for what we're doing here.